Chapter 2, Section 3 of Calculus, Calculating Limits. I'm your host, Dr. D. Let's get started here. Okay. Today's lesson, in the book there are a bunch of limit laws, and they're really almost common sense. Take a look at page 104. On page 104, we have a list of limit laws. Number 1 says that if you've got the limit as x approaches a of a sum of two functions, then you can take the limit as x approaches a of f of x and add that to the limit as x approaches a of g of x. So basically what it means is, if you have a limit of a sum of functions, take the limit of each function and add them up. Or over on page 105 it says, the limit of a sum is the sum of the limits. Then number 2, same thing with subtraction. Number 3, same thing if there's a constant multiplied by the function. Basically, you can take the limit of the function and then multiply by the constant. Number 4, if you have a product of two functions, then take the limit of each function, multiply them together. Number 5, you have a quotient of two functions, take the limit of both functions, divide them, given that the denominator doesn't equal 0 at that point. It's as simple as that. If we continue on, the other limit laws are equally simple. Bottom page 105, limit law number 6. The limit of a function to the nth power, take the limit of the function and take that value to the nth power. And that also goes if the nth power is a fraction. Limit law number 11 is basically that. If you're taking the nth root of the function, then same thing. You take the limit of the function and then take the nth root of that value. Okay, limit laws 7, 8, 9, 10 are pretty simple. The limit as x approaches a of c equals c. Let's take a look at that graphically. If I have a function y equals c, so here's my function y equals c. Now, if I want the limit of this function at some value a, so here's my a value. Well, as x approaches a from the right and the left, what value am I getting? C. C, senor. So that means the limit as x approaches a of c equals c. Because wherever I approach, this thing's going to equal c. Okay, now the limit as x approaches a of x is going to equal a, because you just put in the a value for x, and that's what you get, is a. Limit law number 9, the limit as x approaches a of x to the nth is going to be a to the nth. Same thing, just put in a for x. Limit law number 10, the limit as x approaches a of the nth root of x is going to be the nth root of a. Same thing, put in x, put in a for x. Basically, all those come into the direct substitution property over on page 107. If f is a polynomial or rational function and a is the domain, a is in the domain, then the limit as x approaches a of f of x equals f of a, which means you could just plug in a for x as long as that function is defined at x equals a. Piece of cake. Okay, the only other thing that's, well, real quick, on page 109 is a property that we already learned from last section. The limit is x approaches a of f of x equals L if and only if the left-hand limit equals the right-hand limit. That's the only way a limit can exist. If you're approaching from the left side and the right side, it approaches the same value, then your limit exists. But if I'm approaching from the left side, let's just say I've got a piecewise function here. And I've got this situation. Now, what's the limit as x approaches a? Well, the limit as x approaches a of, let's just say this is y, oops, wrong. This is y equals 3, and this is y equals 5. Well, the limit as x approaches a from the left is 3. The limit as x approaches a from the right of my function is 5. Well, the left-hand limit, the right-hand limit don't equal each other, so that means there is no limit here. That means the limit as x approaches a of f of x does not exist. Okay, that's a piece of cake. So the last thing is the squeeze theorem. Now we're going to get to that at the end of the lesson. What I want to do is just go through the example problems, and you'll see how all these limit laws work. And really, like I said before, if you can substitute the a value in for x, and it's defined, then do it. Okay, so let's do this thing. Okay. Example 1, page 105. The limit as x approaches negative 2 of f of x plus 5g of x. Well, notice, if we look at the limit as x approaches negative 2 of f of x, basically, where is f of x at x equals negative 2? It's at 1. Now, I should say, it's approaching 1 from the left, it's approaching 1 from the right. Now the fact that at x equals 1, f of x really equals 2, that doesn't matter. So here's what we have in example 1. F of negative 2 equals 2. The function value at x equals negative 2 is 2, but the limit as x approaches negative 2 of f of x equals 1. Okay, so if you trace that function from the left, it's approaching 1. You trace it from the right, it's approaching 1. Now at x equals negative 2, it equals 2. But that doesn't have anything to do with the value of the limit. Okay, so we've got the limit as x approaches negative 2 of f of x is 1, and the limit as x approaches negative 2 of g of x is negative 1. So all we do is then add 1 plus 5 times negative 1. So that's going to end up equaling negative 4. Bam. Easy as that. Okay, then part B. The limit as x approaches 1 of f times g. So all you do is evaluate the limit as x approaches 1 of f of x, evaluate the limit as x approaches 1 of g of x, multiply those two numbers together. So as x is approaching 1, the f value is going to be 2. The g value is going to be undefined. So 2 plus undefined equals undefined. So why is the limit as x approaches 1 of g of x undefined? Because the left-hand limit equals -2, the right-hand limit equals -1. They don't agree. That means the limit does not exist. Okay, now C. The limit as x approaches 2 of f over g. So let's go. Limit as x approaches 2 of f is going to be 1.5. And the limit, they're saying 1.4. Okay, we'll go with 1.4. The limit as x approaches g, or limit as x approaches 2 of g, is going to be 0. So we're just going 1.4 divided by 0. That's undefined. So we don't have a value for that. Okay. Example 2. All right, the limit as x approaches 5 of 2x squared minus 3x plus 4. Well, that's a polynomial function. So you know it exists at x equals 5. So all you do is plug in 5 for the x value, and you get 2 times 25 minus 3 times 5 plus 4 equals 39. Piece of cake. Okay, part B. The limit as x approaches -2. Well, first thing I'm doing is I'm plugging -2 in for x on the denominator. If it's not 0, then I'm in the money. And it's not. It turns out to be 11. So all you do is plug it in the top then, and you end up with -1 over 11. That's simple as it gets. Just plug in -2 for all the x's and calculate. That's basically the direct substitution property. Okay, now example 3 is similar to one that we did a couple of days ago. The limit as x approaches 1 of x squared minus 1 over x minus 1. All right, notice if I plug 1 in, I have 0 in the denominator, so that's clearly no good. But if I plug in 1 in the numerator, I have 0 also. So a lot of times when you have 0 over 0, even though that's undefined, there will be an actual solution here. So what do? Well, I'm going to factor the top. So you can see the x minus 1's cancel, and now I have the limit as x approaches 1 of simply x plus 1. And so I don't have to plug in numbers closer and closer to 1 from the left, closer and closer to 1 from the right, and see what it's approaching. I know it's exactly 2, because when I algebraically manipulate this, I can get the basically equivalent function of x plus 1. Now notice, if I were to graph this, what's that going to look like? Well, it's going to look like this. Y equals x plus 1, and at x equals 1, it's undefined. So basically I have a hole right here, but otherwise, this is a linear function except for the value at x equals 1 is going to be 2, but it's undefined there. So it's the same thing as y equals x plus 1, only it's undefined at x equals 1. So if I were to look at this, what's the limit as x approaches 1? Well, as I'm approaching 1 from the left, it's approaching 2. As I'm approaching 1 from the right, it's approaching 2. So the limit equals 2. Okay, cruising onward. Example 4. We have a piecewise function now. the limit as x approaches 1 of g of x, where g of x is x plus 1 if x does not equal 1. Okay, well, that's basically what it looks like. It looks like x plus 1 where x does not equal 1. Now, what if x does equal 1? Then g of x equals pi. So that means 3, 4. So at x equals 1, the function equals 3.14159 approximately. So there's my function. Now, what's the limit as x approaches 1? Well, it's still 2, just the way it was before. Even though the value of the function at x equals 1 is pi, the limit of the function as x approaches 1 is still 2. So the function value has nothing to do with the limit at that point. Okay, cruising onward. Example 5, limit as h approaches 0 of 3 plus h quantity squared minus 9 over h. All right, so what are we supposed to do here? Plug in 0 for h and see what happens. So I get 3 squared minus 9 is 0 over 0, 0 over 0. Remember, that's undefined, but it's a clue that we can fix this and find out exactly what that limit value is. Okay, so what we do is we multiply by the conjugate. So this equals the limit as h approaches 0 of See, here's the point. I need to get rid of the 0 over 0, and the way to do this is to get rid of this squared term, and the way to do that is to multiply by the conjugate. So now notice what happens. I've got a minus b times a plus b, so on top I have limit as h approaches 0 of a squared minus b squared, which is 3 plus h quantity to the 4th minus 81 over h times the quantity 3 plus h quantity squared plus 9, which is going to be okay, so something seems rotten in Denmark. Wait. Ah, rats. Wrong idea. Cut, take 2. We'll edit that out. Now that would have been a major mess. Actually, what we want to do is just distribute that, because it's all set up to eliminate the 9. Yeah, watch what happens. If we just go, this is the limit as h approaches 0 of 9 plus 6h plus h squared. Notice a squared plus 2ab plus b squared. Okay, so now look what happens. 9 minus 9 is 0, so we have the limit as h approaches 0 of 6h plus h squared all over h. Now notice the h's cancel, or if you want, I just factor an h out of the top. And now you can see the h's cancel clearly. So I've got the limit as h approaches 0 of 6 plus h. Now as h approaches 0, that whole thing just equals 6. Okay, now the next example is the one where we want to multiply by the conjugate. So limit as t approaches 0 of t squared plus 9 square root of the quantity minus 3. Okay. So the limit as t approaches 0 copy that right. T squared plus 9. I see. Okay, now, first step, plug in a 0 for t. See what you get. Well, square root of 9 minus 3 is 0 over 0 squared is 0 over 0. So now we multiply by the conjugate. So this is actually the time to do it because we're trying to get rid of the radical. Okay, so now we have don't be doing that stuff. Okay, back to the ranch. So t squared plus 9 plus 3 over t squared plus 9 plus 3. So notice the conjugate, radical minus 3, the conjugate is radical plus 3. Okay, now when I do the a minus b times a plus b, I end up with limit as t approaches 0 of a squared minus b squared. So a squared ends up being t squared plus 9, and b squared ends up being 9 over t squared times the quantity, squared t squared plus 9 plus 3. Okay, so now you see plus 9 minus 9 cancels, the t squareds cancel then, and I'm left with the limit as t approaches 0 of, yeah, let's just do this step so nobody gets confused. Okay, so now we cancel the t squareds and we end up with limit as t approaches 0 of 1 over the square root of t squared plus 9. I keep not making enough plus 3. Yeah, let's just do it like this. Okay, so notice we plug in 0 now, and you get square root of 9 is 3. 3 plus 3 is 6. So this whole thing just equals 1 over 6. And you could have found that out by plugging in values closer and closer to 0 in the beginning, and you would get values closer and closer to 6, but remember, or 1/6. But remember, sometimes that gives you a false value. So sometimes functions get really squirrely when you get closer and closer to that 0 over 0. And the AP exam is a masterpiece of finding those values that you think you can just plug in closer and closer and get something, and it's like, oh, I can use my calculator. Well, you're screwed. So don't fall into that trap. Just know your properties, know your algebra, and you're in good shape. All right. Now, take a look at example 7. This is a classic example. The limit as x approaches 0 of the absolute value of x. Now, first of all, we need to understand the absolute value of x. So, if f of x equals the absolute value of x, basically what that means is f of x equals a piecewise function. It equals x if x is greater than 0, let's say greater than or equal to 0, and negative x if x is less than 0. Now, this confuses a lot of people because you're going like, hey, wait, I thought absolute value was always going to be positive. Well, notice, if x is greater than 0, then yeah, x is positive. But if x is less than 0, then you need to make the negative of that negative to make it positive. So let me show you an example. If absolute value of 5 equals 5, because in this case, 5 is greater than 0, so we're on the top, and so we say, oh, what's the value of the function? It's 5. Well, what if we're taking the absolute value of negative 5? What's that? Well, notice negative 5 is less than 0, so we're on the bottom part of this. So I have to go negative of the negative 5. Negative of the negative 5. And that equals positive 5 again. So that's the strict definition of the absolute value, and you need to remember that. Like, you've seen it for like 2 years in a row. So it's time to actually understand that now. Or put it like this, the people who don't understand it aren't even in the class anymore. Okay, so the limit as x approaches 0 of the absolute value of x. Okay, let's just graph the function. Now, if I want the limit as x approaches 0 from the left, let's see, f of x equals the absolute value of x. So the limit as x approaches 0 from the left equals 0, because as I'm coming from the left, I'm getting closer and closer to y equals 0. And the limit as x approaches 0 from the right also equals 0. Therefore, the limit as x approaches 0 of f of x equals 0. Yeah, if you look at the algebra, the limit as x approaches 0 from the right is going to be the limit as x approaches 0 of x, which is 0. Now the limit as x approaches 0 from the left is going to be the limit as x approaches 0 of negative x, because what's going on from the left? If I'm coming in from the left, I'm really using this part of the function here. So this line right here on the left is y equals negative x, slope of negative 1. And so if I plug in a 0 for that, I get negative 0, which is 0. Okay, take a look at example 8 then. Prove that the limit as x approaches 0 of the absolute value of x over x does not exist. Okay. You know, we're just going to get rid of this part. because we actually are still going to need that part. Okay, so the limit as x approaches 0 of absolute value of x over x. Okay, so what we're going to do first is we're going to say the limit as x approaches 0 from the left of this value. Well, as I'm approaching 0 from the left, I end up with a positive number, a very small positive number over a very small negative number. So let's go and do the actual definition. So the limit as x approaches 0 from the left of this thing is going to be the limit as x approaches 0 of, okay, now, absolute value of x, when x is negative, is going to be negative x. And we just have x here. Okay, now we simplify this. Negative x over x is going to be negative 1. Okay, notice, when I cancel this, now I have a constant. The limit as x approaches 0 of negative 1, well, limit as x approaches anything of negative 1 is going to be negative 1. All right, now we go to the plus side. We go to the right side. Limit as x approaches 0 from the right side, or the positive direction. Well, the definition of the absolute value function is that as I approach x, or as I approach 0 from the right, this is just going to be plain old ordinary x over x, which equals the limit as x approaches 0 of 1, which equals 1. Now, notice what just happened here. We have the left limit equaling negative 1, nice little line there, and then the right-hand limit equaling, what the heck? Who wrote that negative sign? Equaling 1, because limit as x approaches 0 of 1 is 1. Okay, how come none of you told me about that? All right. So, the limit as x approaches 0 of the absolute value of x over x does not exist because the left-hand limit and the right-hand limit do not agree. Okay, so let's cruise onward. We're just about finished here. Example 9 is another piecewise function. So we want the limit as x approaches 4 of f of x. Okay. So f of x equals square root of x minus 4 if x is greater than 4, or 8 minus 2x if x is less than 4. Now the limit as x approaches 4 from the left, that's this part from x equals x is less than 4. I plug in 4 here and I get 8 minus 8 equals 0. or let's just do this, 8 minus 2 times 4, which equals 0. Now the limit, as x approaches 4 from the right of f of x, is the top, because this is where x is positive, so this is the square root of 4 minus 4, which also equals 0. Therefore, the limit, as x approaches 4 of, rats, blew a tire, of f of x equals 0. Now, if you look at the graph on page 110, you can see that graphically. Notice, what is f of 4 here? F of 4 does not exist. Why? Because you've got the square root function for everything greater than 4. You've got the linear function for everything less than 4. But at 4, you have no definition at all. So that means there is no value when x equals 4 of this function. But the limit still equals 0. And you can see that as you approach x equals 4 from the left, the function value is getting closer and closer to 0. As you approach x equals 4 from the right, the function value is getting closer and closer to 0. At x equals 4, the function is undefined, but we don't care. So that's it. All right. One more thing, and then we hit the beloved squeeze theorem. Okay. Example 10, the greatest integer function. We know and love that from math analysis last year. Let's put that on the graph because that is important. And let's actually get a graph out here. Where did my graph go? I have it on here someplace. Let's see. Oh, wait a minute. Here we are. Okay. That's it. Okay. Yeah, we got it. Okay, so f of x equals the greatest integer function. These are just brackets with a double line there. You remember this from math analysis. Once again, most people who don't remember it from math analysis aren't in the class anymore. So what this means is f equals the greatest integer that's less than or equal to x. So if I make x 0, the greatest integer less than or equal to 0 is 0. If I make x 1/2 or 0.5 or 0.6, 0.7, 0.8, 0.9, though the greatest integer that's less than or equal to all those decimals is going to be 1, or is going to equal 0. Now when I get to 1, then it jumps up to the greatest integer less than or equal to 1 is 1. The greatest integer less than or equal to 1.1, 1.2, 1.3, 1.4 up to 1.9 is still 1. Now when I get to 2, it jumps up to 2. So this is basically my greatest integer function like this. And I can go back the other direction. If x is -1, then my value is -1. If x is -0.5, 0.9, well, the greatest integer less than or equal to negative 0.9 is still negative 1. And so it goes back this direction. So a beautiful work of art. A staircase with slope 1 that goes through the origin. All right, now, we want to know the limit as x approaches any integer. So the limit as x approaches 3. Let's see. Yeah, okay, that's what we're doing. So the limit as x approaches 3 of f of x equals what? Well, every time we have a limit we're not sure of, we need to check the left-hand limit, the right-hand limit. So the limit as x approaches 3 from the left, well, okay, let's go to 3. Here's x equals 3. Now, if we approach that from the left, then we're approaching the value y equals 2. As I approach this function, x equals 3 from the left, I'm getting closer and closer to y equals 2. Now, even though at x equals 3 it doesn't equal 2, it's approaching 2 from the left. Now, the limit of the function as x approaches 3 from the right is going to equal 3. Because as I'm approaching 3 from the right, I'm approaching the value of 3. Now, the left and the right-hand limits don't agree, so the limit as x approaches 3 of f of x does not exist. Oh, and that's, it says equals does not exist. It just plain does not exist. Okay, so what we can say then is any greatest integer function, the limit as x approaches any integer is going to be undefined or does not exist. Because at any integer you're going to have a different right and left limits. So that's it. Last idea here is the squeeze theorem. Now this is a little bit more difficult to understand, but take a look on page 110 at the bottom. If f of x is less than or equal to g of x, which is less than or equal to h of x. All right, well, let's absorb that before we go on. So we've got figure 7. F is the blue function, g is the red function, h is the yellow function. Notice f is below g at every point. Well, actually, I should say it's either less than or equal to. So notice that at x equals a, f and g are equal. Now, g is below h at every point, at least that we're interested in, with the exception of a, where it's equal. So that satisfies the hypothesis of this theorem. F is less than or equal to g, which is less than or equal to h. Now, the second thing that has to be true is the limit as x approaches a, or as x approaches the value we're interested in, is equal to the limit as x approaches a, or the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x. So notice h and f are above and below g. So h and f kind of squeeze g in the middle. So if that's the case, that h is above and f is below and g is in the middle, and you know the limit as x approaches a of the top function and the bottom function, then you're guaranteed that the middle function has to be that same limit. So here's where this is good, is where you have a function that is undefined at the limit, but you know the top function, you know the bottom function are that limit, and then you have the middle function. All right, so check out example 11. Show that x approaches 0, the limit is x approaches 0 of x squared times sine 1 over x equals 0. Now, notice sine of 1 over x. Well, that's sine of 1 over an infinitesimally small value. Well, what's that? 1 over an infinitesimally small value is an infinitely large value. So what that's saying is, what is the sine of some value as that value gets bigger and bigger? Well, it's undefined because sine curve goes up to 1, down to -1, up to 1, down to -1, 1, -1, 1, -1. And if I keep going forever, it's never going to approach anything. Now, if I look at this function,